One of the things students sometimes have trouble with are predicting the products of a single displacement reaction or a double displacement reaction, and then balancing the equation and determining the states of matter. So we'll do a couple more practice problems of single displacement and double displacement reactions. So if we have a typical single displacement reaction, what's going to happen is the component by itself is going to come in and displace part of this compound here. So our zinc is going to replace the hydrogen, and it's going to be with the chlorine, and the hydrogen is going to be by itself. Right. So one of the products is now zinc will want to be with this chlorine, and this is an oxidation reduction reaction as well, because our zinc has a 0 and it's going to 2+. We cross multiply, that tells us we need 2 chlorine and 1 zinc. So one of our products is going to be zinc chloride. And chlorides tend to be, our halides tend to be aqueous, and there's no exception for zinc in that rule. And the other product is going to be hydrogen is now going to be by itself, and we have to remember that hydrogen is going to be diatomic. All right. So now we've predicted our two products. Now we have to balance our equation. So we're trying to balance our zinc, our hydrogen, and our chlorine. Here we have 1 zinc atom, 2 chlorine atoms, and 2 hydrogen atoms. Here we have 1 zinc, 1 hydrogen, and 1 chlorine atom. So we have odd numbers here, even numbers there. We're going to have to make these odd numbers even. So we put a coefficient of 2 in front of our HCl. We still only have 1 zinc atom, but now we have 2 hydrogen and 2 chlorine, and now we have a balanced chemical reaction. So that would be the product of that single displacement. Here's another single displacement reaction. This magnesium is going to come in and replace this copper. We need to remember magnesium is in group 2, so it's going to form a +2 cation. Our nitrate from our polyatomic ion table has a charge of -1, so we need 2 of these for every 1 of those. So one of our products is going to be magnesium nitrate, and now this copper is going to be by itself. So we have copper solid, and nitrates tend to be soluble, and there's no exception for magnesium, so we'd expect this to be aqueous. Now we have to look to see if our equation is balanced. So we're trying to balance our copper, our magnesium, and we could treat this nitrate as one group that we're trying to balance in this instance. So here we have 1 magnesium, we have 2 nitrates, we have 1 copper, here we have 1 magnesium, 1 copper, and 2 nitrates. So our equation is balanced at this point. All right, one more single displacement reaction. We're going to put a piece of aluminum in some hydrochloric acid. The aluminum is going to displace the hydrogen. It's going to be with the chlorine. From what we've learned earlier in the semester, aluminum is going to form a +3 charge. Chlorine is a halogen, so it's going to be -1. So we need 3 of these for every 1 of those. So one of our products is going to be AlCl3. Chlorides tend to be aqueous, and there's no exception for aluminum. Our other product is going to be hydrogen by itself, and hydrogen is diatomic, so H2. Right? So those are going to be the products we're going to predict from the single displacement reaction. Now we're going to try to balance our aluminum, our hydrogen, and our chlorine. So on this side of the arrow we have 1 aluminum atom, we have 3 chlorine, and we have 2 hydrogen. On this side we have 1 aluminum atom, 1 hydrogen, and 1 chlorine. All right, and so we might be tempted to put a 3 here, and we would end up with 3 chlorine, but the problem becomes we would still have an odd number of hydrogen and an even there, so we need to make this an even number. So we're probably going to have to start with something like a 6 here in front. So we would still have 1 aluminum, 6 hydrogen, and 6 chlorine. Now we have even numbers over here. All right. If we come back to our other side of the equation, now we have 6 chlorine on this side. We only have 3 here, so we put a coefficient of a 2 in front of the aluminum chloride. So now we have 2 aluminum atoms, 6 chlorine atoms, and we still have 2 hydrogen atoms, so we're still not quite balanced. We could do a couple steps next. We have 6 hydrogen here, we have 2 over here. We could put a coefficient of a 3 in front of this hydrogen. So now we still have 2 aluminum atoms. We have 6 hydrogen atoms, and we have 6 chlorine atoms. So our hydrogen and chlorine are balanced, so now all we have to do is balance our aluminum. We put a 2 there. We have 2, 6, and 6, so we have our balanced single displacement reaction. All right, now we're going to switch gears to a double displacement reaction. And remember, in double displacement, this cation is going to want to be with this anion. This cation is going to want to be with this anion. So we're just switching. So we need to look at what we have here. We have barium with a 2+, and it's going to now want to pair with the phosphate. From our polyatomic ion table, we have a 3- charge. So we're going to need 2 of these and 3 of these. So one of our products is Ba3 PO42. And the other one, now the sodium has a +1 charge. It's going to bond to be with the chlorine, which has a -1. So those are going to go together 1 to 1. Right? So we could do 2 different things here. We could first balance equation, or we could predict the solubility. So we need to predict the states of matter of our 2 products. So we need our solubility table. And if we look at barium phosphate, our rule for phosphate is phosphates tend to be insoluble. There's no exception for barium, so this should be a solid. Our rules up here say that type 1 metals, such as sodium, tend to be soluble, which means they're aqueous, and halides tend to be aqueous, so we would expect sodium chloride to be aqueous. So we predicted the products and their states of matter. Now we need to balance our equation, and we could treat this phosphate as one group here. So here we have 3 barium atoms, we have 2 phosphate, we have 1 sodium and 1 chlorine. Over here we have 1 barium, 2 chlorine atoms, 3 sodium, and 1 phosphate. So we're pretty far afield as far as being balanced. So we have an odd number of barium, but we could end up with an odd number on both sides. That is fine. So we could start by putting a 3 here in front of our barium chloride, and now we have 3 barium, 6 chlorine. We still have 3 sodium and 1 phosphate. So we're still not quite where we need to be here, but our barium are now balanced. So if we have 2 phosphate on this side and only 1 over here, then the next thing we could try is putting a 2 in front of this number. Right? And so that didn't change our barium. We still have 3 of those and 6 chlorine, but now we have 6 sodium atoms, and then we have 2 phosphates. So our phosphates are balanced and our barium are balanced. The only thing that's not balanced here are our sodium and chlorine. So we have 6 sodium and 6 chlorine on this side, so we can put a 6 here. Now we have 3 of these. We have 6 chlorine atoms, 6 sodium atoms, and 2 phosphates. So now we have a balanced chemical reaction. Here's another double displacement reaction that we can try to predict the products. So here we have silver nitrate with potassium carbonate. Now the silver cation is going to want to be with the carbonate anion. This potassium cation is going to want to be with the nitrate. So from previous studies, we know that silver is going to form a +1. From our polyatomic ion table, carbonate is going to be a 2-. Our potassium is in group 1, so it's going to have a +1 charge, and our nitrate from our polyatomic ion table is going to have a -1. So these are going to go together 2 to 1, right? If we cross multiply, so we need 2 silvers for every carbonate. That's one of our products. And the other one is the potassium and the nitrate go together 1 to 1, KNO3. So those are the products of our double displacement reaction. Now we want to determine if they're going to be aqueous or solid. So here it says in our bottom corner that carbonates tend to be solids. There's no exception for silver, so we'd expect this to be a solid. Up in this corner it tells us that type 1 metals like potassium tend to be aqueous and nitrates tend to be aqueous, so we'd expect this to be aqueous. Right, now we have to balance our equation. So we are trying to balance silver, and we'll treat nitrate as a group, and we'll treat the carbonate as a group. Right. Right, so on this side we have one silver atom, we have one nitrate polyatomic ion, we have two potassium, and we have one carbonate. Over here we have two silver, we have one nitrate, we have one potassium, and one carbonate. So we've got some work to do in our balancing. One thing, we have two silver here, we have an odd number here, so I'd probably start putting a 2 coefficient in front of that silver nitrate. That would give us two silver atoms, two nitrates, we have two potassium, and one carbonate. So we've kind of started to get a little more in balance here. Right, so now our potassium isn't balanced, and our nitrate are not balanced, but those are both in the same compound. So if we put a 2 coefficient in front of the potassium nitrate, we still have two silver. Now we have two nitrate, two potassium, and one carbonate. So now we have a balanced chemical equation. One last double displacement to practice here. So now the calcium is going to want to be with a phosphate. Calcium is in group 2, so it has a +2. Our phosphate has a -3. Our lithium is in group 1, so it has a +1. Our chlorine has a -1, so those are going to go to the 1 to 1, and these are going to go to their 2 to 3. So one product would be calcium phosphate. So we need 3 calcium for every 2 phosphate. And the other product is going to be the lithium and chlorine going together 1 to 1. Now if we want to predict if we're aqueous or solid, we would kind of look at our chart here and say that group 1 metals like lithium tend to be soluble, chlorides tend to be soluble, so we'd expect lithium chloride to be aqueous. Down here we say phosphates tend to be insoluble. There's not an exception for calcium, so we'd expect that to be a solid. So we predicted the products and if they're going to be aqueous or soluble. Now we have to balance our equation. So we're trying to balance calcium, chlorine, lithium, and we're going to keep this phosphate as one group and just balance it as a group. So here we have one calcium atom, two chlorine atoms, 3 lithium atoms, and 1 phosphate group. Here we have 3 calcium, 2 phosphate, 1 chlorine, and 1 lithium. All right, so we're pretty far from balanced here. We're running out of time in this video, so I will balance it just quickly here. We're going to end up needing a 3 here, a 2 here, and a 6 here, and then we end up with 3 calcium on this side, 6 chlorine, 6 lithium, and 2 phosphates. And on this side we still have our 3 calcium, our 2 phosphates, and now we have 6 lithium and 6 chlorine. So that's your balanced equation.